Today we're going to make protein synthesis so memorable, you'll never forget it. Forget boring textbook definitions. We're going on a journey from a library to a kitchen in Brooklyn. By the end of this video, you'll understand DNA replication, transcription, and translation like never before. Are you ready? Let's dive into the most delicious biology lesson you've ever had. Imagine your cell is a city, and in the center of this city is a massive library. This library is your nucleus. Inside this library, there are thousands of cookbooks stored on shelves. Each cookbook is a chromosome, and each recipe in those cookbooks is a gene. But here's the thing, these aren't just any cookbooks. These are the master cookbooks containing the DNA, the complete instructions for making every single protein your body needs. Now, the city needs to make proteins. These are the meals that keep your body functioning. So let's see how this happens. Enter our first character, messenger RNA or mRNA. Think of mRNA as a student who needs a recipe to make a specific protein. The mRNA walks into the library and says, "Hey, I need the recipe for insulin," or "I need the instructions for hemoglobin." The mRNA approaches the shelf and reaches for the master DNA cookbook, ready to copy a specific page. That's the gene with the code it needs. But wait, something happens. The librarian stops the mRNA and says, "Hold on, you cannot take or write directly from the master cookbook. These are the originals. We must protect them." So what does the librarian do? The librarian makes a photocopy of the entire cookbook first. This is called DNA replication. Here's how the photocopying works. Step 1. Opening the book, DNA helicase. The librarian uses a special tool called DNA helicase. Think of this as the machine that unzips or opens the double-stranded DNA book. The two strands of the DNA double helix separate, creating a replication fork. The book is now open and ready to copy. Step 2. The photocopying machine. DNA polymerase. Now comes the photocopying machine itself. This is DNA polymerase. DNA polymerase reads the original DNA strands and creates new complementary strands by adding matching nucleotides. It's literally making a perfect copy of each strand. If the original says A, it adds T. If it says G, it adds C, and vice versa. The photocopying machine works on both strands simultaneously, creating two complete copies of the DNA. Step 3. Binding it back together. DNA ligase. After photocopying, we have some gaps and fragments that need to be sealed. Here comes DNA ligase, the GLUE or binding machine. DNA ligase acts like a stapler or tape dispenser, joining all the DNA fragments together to create a complete, continuous strand. It seals the backbone of the newly formed DNA. Boom! Now we have two complete copies of the DNA cookbook, the original and the photocopy. Both are identical and perfect. Now the librarian says to the mRNA, "Okay, you can copy the recipe you need from the photocopy, not the original." This process of copying a specific page, a specific gene, from the DNA is called transcription. Here's what happens. The mRNA finds the exact gene it needs. The DNA strands open up at that specific location. An enzyme called RNA polymerase reads the DNA code and creates a complementary mRNA strand instead of thymine. RNA uses uracil. So if DNA says TSAGT, the mRNA copies it as AUGCCA. Memory trick. Transcription equals making a transcript or written copy of the recipe. The mRNA now has the recipe written in a language the kitchen can understand. Remember, all of this, the photocopying and copying the recipe, happens inside the nucleus, inside the library. The mRNA now has its recipe. It's like holding a piece of paper with cooking instructions. It exits the library through the library doors. These are the nuclear pores, and enters the cytoplasm, the main area of the city. The mRNA is on a mission. Get to the kitchen. The mRNA arrives at the kitchen. This is the ribosome. But here's the fun part. This kitchen is located in Brooklyn, and Brooklyn represents the rough endoplasmic reticulum, or RER. The RER is studded with ribosomes, making it the perfect place for protein production. Now, the mRNA has the recipe, but it needs ingredients. Enter transfer RNA, or tRNA. Think of tRNA as the delivery person or grocery shopper. The tRNA molecules go to the market and pick up groceries. These groceries are amino acids. Each tRNA carries a specific amino acid based on the code it reads on the mRNA recipe. The tRNA reads the mRNA code in sets of 3 letters called codons. If the codon says August, tRNA brings methionine if it says UU. tRNA brings phenylalanine if it says GGC. tRNA brings glycine. One by one, multiple tRNA molecules bring the correct amino acids to the ribosome kitchen. Now comes the chief chef. This is the ribosomal RNA, or rRNA. The rRNA reads the mRNA recipe step by step and uses the amino acids brought by the tRNA to cook up the protein. The rRNA links the amino acids together using peptide bonds, creating a long chain. This chain folds into a specific 3D shape, and voila, you have a protein. This process of making the protein from the mRNA code is called translation. Memory trick. Translation equals translating the recipe language into an actual meal. The protein meal is now cooked. But we're not done yet. The freshly made protein needs to be properly packaged and prepared for delivery. Where does it go? It travels to the storage and packaging center. This is the Golgi apparatus. Think of the Golgi as a warehouse or distribution center. Here, the protein is modified, packaged into vesicles labeled for its destination. Once properly packaged, the protein is shipped out of the cell through a process called exocytosis. The vesicle fuses with the cell membrane and releases the protein outside the cell to wherever it's needed in the body. Maybe it goes into the bloodstream, maybe to another organ, but it's now ready to do its job. Let's recap this incredible journey. Classical building the library. Master DNA cookbook stored here. Open book DNA replication. Photocopying the entire cookbook. DNA helicase equals open/unzips the book. DNA polymerase equals photocopying machine. DNA ligase equals glues/binds it back together. Memo transcription. mRNA copies a specific recipe from the DNA photocopy. Happens in the nucleus door. mRNA exits through nuclear pores to the cytoplasm. Cooking the kitchen. Located in Brooklyn shopping cart. tRNA equals grocery shopper. Brings amino acids from the market. Man cook. rRNA equals chief chef. Links amino acids to make protein. Counterclockwise arrows button translation. Converting the mRNA recipe into actual protein package. Golgi apparatus. Packages and modifies the protein delivery truck. Exocytosis. Ships the protein out of the cell. Ultimate memory hook. Library photocopy. Copy recipe. Exit kitchen. In Brooklyn shop groceries. Cook package ship. Nucleus replication transcription. Cytoplasm ribosome on RER tRNA. Brings amino acids. Translation. Golgi exocytosis. And there you have it. Protein synthesis from DNA to finished protein. Explained through the most memorable story ever. If this helped you understand molecular biology better, please smash that like button. Drop a comment telling me your favorite part of this analogy, and hit the notification bell so you never miss my educational content. Want access to exclusive study materials, detailed notes, and premium biology content? Join my YouTube membership today. Also, connect with me on Instagram at officialder.ray for daily science tips, study hacks, and behind-the-scenes content. Thank you for watching. And remember, biology is just a story waiting to be told. Keep studying, keep crushing those exams. See you in the next video.